Hey everybody, it's Mrs. Harbin. We're going to do some predicting products and categorizing reactions and talking about states of matter. So we're going to also look at endo and exotherm right now. So please read chapter 11, sections 2 and 3 to help yourself understand this information. And so let's go back to the 5 types of reactions. There's combination synthesis, decomp, single replacement, double replacement, and combustion. But now you're only going to get half the reaction, the reactants, and you're going to have to predict the product. So you'll need a periodic table with you at all times. Okay, so if I look at this, I see there's 2 elements. So I know that this is a synthesis reaction. If I look here, I see it's 2 elements, synthesis, 2 element synthesis. So now is the time for the periodic table to come in. And what the periodic table is going to tell us is that these 2 elements are unstable when they're by themselves, so we're going to come together to make an ionic compound. The metal's going to come first. We look at the periodic table. When you see sodium on the periodic table, it's going to make a +1 charged ion. Sulfur is going to make a -2 charged ion. So we're going to get Na2S because sodium is a +1, sulfur is a -2. So we need 2 of the sodiums. And then we're done predicting the products for that reaction. But it's not balanced, so we'll practice balancing later. But right now, what we're doing is we're writing the products. So element lithium, element fluorine. Lithium from the periodic table, if it loses 1 electron and fluorine gains 1, it's going to make F. So that's going to be the product when those 2 elements combine. Right, oxygen and barium. Barium from the periodic table loses 2 valence electrons to be more stable. Oxygen gains 2 valence electrons to be more stable, and you get BAO. All right, so first you have to cancel the charges to make the products for synthesis. Then you can go back and balance them. So now I have 2 sodiums on this side, so if I put a 2 there, 2 sodiums, 1 sulfur, 1 sulfur. Do not balance an equation until after you have correctly written the chemical formulas of the products, okay? This has to be LIF because it's a +1 and -1. Use your ions from the periodic table. It tells you why they become more stable. Lithium, when it loses 1, has a full set. Fluorine, when it gains 1, has a full set. Okay, same thing. And now we need to put a 2 there, a 2 there, to make sure we didn't lose any atoms. All right, over here, we need to make a 2 there and a 2 there. But your first job is to write the correct chemical formula. Oh, look, it's 3 reactions, and they all only have 1 reactant as product, so they must all be decomposition. Decomposition reactions will break down into their elements. So the elements are mercury and oxygen. But wait, oxygen, when it's by itself, is never really by itself. It needs to have a 2 next to it. Okay. Oxygen is also a gas. Mercury is a liquid metal, and mercury oxide is a solid because it's an ionic compound. So then we can look at this next compound. 1 compound is a reactant, the decomp. So we break it into its elements, nitrogen and hydrogen. But wait, are any of these diatomic? You betcha. Nafkuber, the N and the have 2's next to them because whenever they bind themselves, they're never really by themselves. Both of those are gases, and this I'll tell you the gas. And so then we've correctly decomposed it. Aluminum sulfide compound, 1 reaction breaks down into its elements. So we have aluminum and sulfur. Okay. Now aluminum or sulfur, neither are diatomic, so we're done with that. But then we need to say aluminum is a metal, so it's going to be solid. Sulfur is a non-metal, it's going to be solid. And then we can put in some coefficients now. We need 3 of those and 2 of those to balance the equation. In this one, we need 2 N's, and now we need 6 H's. In this one, we need 2 HGOs and 2 mercury. So, step 1, write down the correct product. Step 2, balance the equation. Those are all decomp. Okay, this next one is a little different. Single replacement. So in a single replacement reaction, first of all, you have to recognize it, element, compound. And after you recognize it, you have to decide if it's going to happen. So you have to see if the single element, the one that's by itself, can replace the one it's trying to kick out. So lithium's a metal. The only thing he could try to replace is a metal. So you see lithium and silver. Lithium's higher up. It's more active, so it will replace silver. Then you have to cancel the charges. So lithium needs to go with nitrate. If you look on the periodic table, lithium's a +1. Ion sheet says nitrate is a -1. So you get LiNO2. And then what happens to the silver? It gets kicked out as well. Right. Cobalt and calcium. Why am I just underlining the first ones? Because cobalt's a metal, so you have to try to replace a metal. So cobalt is right here, calcium's here. Guess what? Cobalt cannot kick out calcium because cobalt is not more active. So this, even though it looks like it's going to be a single replacement, actually is a no reaction. Okay. An element and a compound. So you're thinking single replacement. Me too. So let's look. Let's see if the element, the one that's by itself, first of all, it's a non-metal. So we're going to look at the non-metal activity series, and it has to try to kick out the non-metal. So let's see, chlorine is below fluorine. So that means fluorine's more active. So this is a no reaction. No reaction because fluorine does not have the ability to kick out fluorine because it's less active. Okay, so single replacement is an element in a compound. Okay, then you check the activity series, see if it works. So look at what we got here. We got an element and a compound, single replacement. Then what do I look for? Well, barium's a metal, so I look to see if it's higher than gold. Barium, where is it? Barium, gold. So guess what? Barium can kick out gold. So barium's going to kick out gold, and it's going to go with sulfate. Barium from the periodic table when it makes an ion is Ba. Sulfate is -2, +2, -2. You're going to get BaSO4. What gets kicked out is the gold. Look, there's no charge on gold because when it gets kicked out, it's an element. Sodium and magnesium chloride, element, compound. This is a metal, so it can only try to kick out the metal. Let's go back and see. Here's sodium. Sodium's here, magnesium here. Sodium can kick out magnesium because it's higher. So now we go to the periodic table. We get sodium a +1 and chlorine a -1. So we get an NaCl. Who gets kicked out? Bye-bye magnesium. You just got kicked out. All right, why did I put NaCl together as NaCl? Because it's a +1 and a -1. Then I could go back and balance the chemical reaction using coefficients. Right? So I'm going to need 2 of these, so I get 2 chlorines. That also gives me 2 sodiums, and now I'm done. Okay, element compound. Fluorine is a non-metal, so I have to look at the non-metal part of this compound. And then I'm going to look on the activity series to see if fluorine, the one by itself, is higher than bromine. Let's look. Fluorine, higher than bromine. Yeah, it's going to react. Woohoo. Whoops, hey, come back. Okay, so fluorine's going to have to kick out bromine. Now I go over to the side and I say to myself, all right, we got sodium, it's a +1, and now fluorine is a -1. So I'm going to get NaF. Why? +1, -1. That's why. That's it. That's why. Okay. Who got kicked out? Well, bromine got kicked out. And I look and I say, but wait. Bromine's one of the diatomics, so I have to put a 2 next to it when it's an element. And I have to use NaF as NaF because it's a +1, -1. So that's not balanced, so I need coefficients. I'm saying, well, I need 2 of those to get me 2 bromines, and that's going to make me have 2 of those. So I have 2 sodium, 2 sodium, 2 bromine, 2 bromine, 2 fluorine, 2 fluorine balanced. Okay. Finally, we have manganese, which is a metal, so it's got to try to kick out element compound. It's going to try to kick out the metal. So, hey, what was I looking for? Oh, manganese. Manganese right here. All right. What's it trying to kick out? Aluminum. Where's aluminum? Where is aluminum's above it? Wah, wah, wah. Sorry, manganese, you can't do it. This is going to be no real. All right, so how did I know they were single replacement? One element, one compound. Then I look to see if the element by itself can kick out this element that it's similar to. Metals can only kick out metals. Cancel charge and move on. Okay, next we're going to have to refer to what is a precipitate here. A precipitate is something that's insoluble to solid. It's shown as a down arrow or a S in the reaction. AQ is aqueous, which is dissolved in water, and S is solid, not dissolved in water. So this is a solid precipitate. This is AQ. Oh yeah. So why am I talking to you about this? Well, in a double replacement reaction, one of the reasons it happens is because a precipitate forms or solid forms. So how do you know which product in a double replacement is going to be the solid? We'll use the charges of the ions. We're going to use Coulomb's law. Right? If these charges are really high number charges, they're going to stick together and be a strong, strong bond. Okay? They're going to have a strong force of attraction. So what you have to do is multiply the charges of the ions, and if you get 4 or greater, that compound will be the precipitate. If you multiply the charges of a compound's ions and it's 3 or less, it's going to be aqueous. How do we know that? Well, let's look. So NaCl, is that going to be aqueous or a solid in a chemical reaction with water around? Well, if you have a +1 times -1 equals 1. Why just 1? Because it's absolute value. So this is going to be an aqueous substance in a chemical reaction because the charges aren't big enough to make it solid. Okay. Oh, this should be a lowercase subscript of 4. Okay. So we have Na, which is a +1 charge, and phosphate's -3. So we have +1 times -3, but it's absolute value, so we get 3. So what does that mean? 3 or less means that Na3PO4 is going to be aqueous or insoluble because the charges aren't great enough to fit them together. It's a solid. All right, here we go. We have Ca, which is a +2, and oxygen, which is a -2. We multiply them together, and we get a total of 4 because it's absolute value. 4, what does 4 mean? If the product's 4 or greater, CaO will be a precipitate or a solid. That means the same thing. Okay, let's see how we can use this. First of all, what type of reaction is this? Look, it's got 2 compounds, compound. So then you do the switcheroo and cancel charge. So lead is a +4. I know that because chloride's a -1. H is a +1. Phosphate's a -3. So now I got to put them together in a different way. But once it's first, it's always first. So my +4 lead, all right, has to go with my -3 phosphate. So I'm going to need 3 of those for +12. Phosphate, I'm going to need 4 of those. Okay, and then my +1 and my -1, which I'm going to HCl. Now, how do I know which one of these is a solid and which one's aqueous? Well, a +4 times a -3 gives me whopping 12. All right, that's much greater than 4, so that's going to be solid. And I can assume this is aqueous, but it's a +1 and a -1. So I get 1 as absolute value, so I can make it aqueous. Okay, K2SO4, compound switcheroo. So we have Mg, which is a +2, and F's a -1. K is a +1, sulfate's a -2. So now I got a switcheroo. Once it's first, it's always first. So I'm going to put the K together with the F, a +1 and a -1. And I'm going to put the Mg with the SO4, +2 and a -2. Luckily, no subscripts on this because all the charges cancel. And then I'm going to check charges. So this is a +1. 1 times 1 is 1. So that's going to be aqueous. And this is +2 and -2 equals 4. That's absolute value. So this is going to be a solid because it's got the high Coulomb's law force charge. Okay? All right, so we have 2 reactants, 2 compounds, -2 and +2. This is a +2 and -1. So I'm going to do the switcheroo. So magnesium comes first, and it's with chlorine. So that's a +2, so I'm going to need 2 chlorides to cancel it out. And then calcium and carbonate, it's a +2 and a -2. So they go together as CaCO3. So now I got to check which one's going to be the precipitate. So I have +2 times -1, and that gives me absolute value, gives me 2. And then +2 times -2, absolute value gives me 4. Lucky winner, solid A2. Okay. So, stating your success. Whenever we're doing these reactions, the metals are going to be solid. Any element that's a metal is solid except mercury is a liquid. Diatomic elements are all gases except bromine is a liquid and iodine is a solid. And a compound. How do you recognize them? They usually have a metal in them or a polyatomic ion. If you're in a decomp reaction or combination, they're going to be solid. They're going to be aqueous when the reactant's a double replacement and single replacement. All right. But in the products of double replacement, one of the ionic compounds is going to be a solid. Combustion gives gases. Now, we didn't even talk about combustion because here's how you recognize them. You see something with carbon, C2H6, we'll say, plus something with oxygen gas. It has to have oxygen gas. And guess what? You don't even have to think about it. All you have to do is write down CO2 and H2O. And they're both going to be gases. Okay? So CO2 and H2O every time for combustion. All right, this is a list of all the ones we're going to practice when we're in class. Okay, so some of the keys to success are You see a synthesis, oh my gosh, I can't even talk. See a synthesis reaction, cancel the charge for the product. It's going to be an ionic compound, cancel its charge. Decomposition, look for your diatomics because you're going to get elements. Some of them will be diatomic, those 7. In a single replacement, use the activity series to see if it's even going to work. Check the right series, the correct one. If your element's a metal, check the metal series. If your element's a non-metal, check the non-metal series. Double replacement, cancel your charges, and one product's usually going to precipitate. Okay, combustion, recognize, and move CO2, H2O are the products. Okay. All right. So something new here we're going to talk about is called delta H, and that's what you say. You say delta H. What is delta H? It's a measure of internal bond energy. Okay. So there's something holding your reactants together called a bond, a chemical bond. There's also things that hold products together called chemical bonds. But in order for a chemical reaction to happen, the chemical bonds of the reactants have to break, and then the chemical bonds of the products have to form. Okay, so anytime you have reactants, you might have things bonded together. You have to always add energy in to break the bond. So look at this energy atom always goes uphill first because you have to break the original bonds, right? Then new bonds form. Okay. So say we get, those are the products. So first you got to break these bonds. So energy uphill first to break the bond, downhill to make new bonds. It's like the release of energy when new bonds form. So here's the thing. If the reactants are more stable, it's going to take a lot of energy to break their bonds. The products are less stable, they're not going to lose a lot of energy when they form. Okay, this is called an endothermic reaction because it takes more energy to break the bonds than gets released when new bonds form. Okay. All right, so what about this reaction? We got to break all of these bonds. So which way is our energy going to go? It's going to go uphill first to break the bonds. Now, new bonds are going to form. Okay, we get some new bonds forming here. When these new bonds form, these products are more stable, so they have lower energy. So a lot of energy is released when these bonds form. So we call this kind of reaction exothermic because what happens to the extra energy? This extra energy is released as heat. That's the delta H. So break the bonds, add energy in to break the bonds, but then look at downhill, a lot more energy gets released. The difference between where the reactants and the products are is called the heat, the delta H, or the measure of the bond energies. Okay, let's go back to this one and find the delta H. If you notice, overall delta H, you have to add energy in, so it's going to be positive. Over here, the delta H energy is going to be released. It's going to be negative. Okay, so endothermic, uphill, downhill, but the products end up higher. Exothermic, uphill, downhill, and you got to go low with the products, and energy is released. Okay, so how would that look? Or why does this happen? Breaking bonds is like breaking bones. Your bone doesn't break just, for nothing. What happens is energy gets added to that and it cracks. Breaking bonds requires energy. I hope breaking bonds requires energy, so does breaking bones. So anytime a bond has to break, you have to add energy in. New bonds forming releases energy. Right? Otherwise, they wouldn't even form. It's always downhill to make the products. So breaking bonds is endothermic, or breaking bonds requires energy. Add energy in, add in. Bond formation releases energy. Okay. So what does that mean? There's two things that can happen. You could have an endothermic reaction, and overall the heat goes up, means the products go higher. So here's what your energy diagram would look like. You end up in endo, end up. That reaction would feel cold to us because the system's taking in heat. The heat would be like a reactant, and it's going to be absorbed, and then your delta H is going to be positive. That's the total opposite for exo. Exothermic reactions, heat goes out of a reaction, it's going to feel hot. the heat term is going to be on the product side, and it's going to release heat. And the delta H is going to be negative. All of these are signs of exothermic. You feel the heat, exo. You look at the reaction and you see heat in the products, exo. Heat's being released, exo. Negative delta H, exo. See an energy diagram go low, that's exo. Okay, so here's some reactions. We just got to identify if they're endo or exo. So we have heat plus that gives us that and that. Okay, we'll get the old double replacement going on. Where's the heat? The heat's on the reactant side. It's added in. So this is endothermic. Add in, endo. Okay. Zinc and that. Hey, that looks like single replacement. Hey, heat's on the product side. Arrow points to product. So it's leaving. It's exothermic. Okay. That's my phone. We'll get it in a second. Okay, so here's the heat. It's on the reactant side. So it's endothermic. Over here, hey, there's no heat in this reaction. Right? No heat. But look, it tells us right here that the delta H is positive. Is negative. Negative delta H means okay. So, endo or exo. Here's some more. We'll practice these notes in class. All right. So, hey, just for fun. If Chloe's cool, is she endo or exothermic? She's cool. All right, so she's endo. If Jack is hot, is he exo or endothermic? Exothermic. All right, that was just for fun. All right, so just to sum up everything in this video notes, types of reactions. You recognize each reaction type by the reactants, or you recognize if something's endo or exothermic by using the information. Right? Cancel charges for ionic compounds. Use activity series for single replacement. Use Coulomb's law for double replacement. Combustion is always the same. Carbon dioxide and water are your products. And then endo into exo exit. And it's time for me to exit. Make sure you read chapter 11 and understand all these 3 bullet points, which are objectives for this PowerPoint. Peace out, kids.